Section 3.7, Rates of Change in Applications, Natural and Social Sciences. We now look at how the ideas of rates of change and derivatives apply to a lot of other areas. So first recall the following. Delta x means the change in x, and so we think of that as the difference of two x values, like x2 minus x1. Delta y equals f of x2 minus f of x1, so the difference of two y values. We also might have written at some point b minus a for delta x and f of b minus f of a for delta y. The difference quotient that we've seen is delta y divided by delta x. And we had called this the average rate of change of y with respect to x over a particular interval, in this case x1 to x2. We interpreted that as the slope of the secant line all the way back in section 2.1, and as we took the limit as delta x went to 0, we got the slope of the tangent line, which we then developed throughout chapter 2. That gave us the instantaneous rate of change of y with respect to x, and we wrote dy dx, meaning the derivative of y with respect to x, is equal to the limit as x approaches 0 of that difference quotient, delta y over delta x. So one application that we've actually seen was in physics. We saw that if we called s equal to f of t, meaning s is a function of t, and if that represented the position of some particle, then delta s over delta t represented the average velocity or speed over a time period. And then we called v equal to the derivative of s with respect to t. We called that the instantaneous velocity, meaning the rate of change of displacement with respect to time. The instantaneous rate of change of velocity with respect to time we also saw was acceleration, which meant that the acceleration at time t is equal to the derivative of the velocity at time t, which is equal to the second derivative of the position at time t. So now we're just going to do another example to explore that a little bit more. We had those ideas a little bit ago, but now we're going to go into some more detail and then see how these three functions actually relate to each other. So this example, the position of a particle is given by the equation s equal t cubed minus 6t squared plus 9t. So s is a function of t, and it gives the position of a particle at any time t. So first, part A, find the velocity at time t. So since this says at time t, this is meaning a function where the independent variable is t. So we are looking for v of t, and that is simply just the first derivative of the position function. So s prime of t. And we could just use the power rule that we established at the beginning of chapter 3. So for t cubed, the derivative is 3t squared. And then minus the derivative of 6t squared will become 12t. And then plus the derivative of 9t is just 9. Part B says, what is the velocity after 2 seconds? Meaning at time t equal to 2, what is the velocity? Which just means evaluate the velocity by plugging in 2 for t, which gives us 3 times 2 squared minus 12 times 2 plus 9. This turns into 3 times 4, which is 12, minus 12 times 2, which is 24, plus 9. And that would give us negative 3. And we do want to have some units here. So we can assume that we're talking about meters for position and seconds for time, because we've seen that before when we've talked about position, velocity, and acceleration. So how about meters per second? And then the second part of part B is what about after 4 seconds? So for this, t is equal to 4. So we are wanting to find the velocity at time 4, which again would just be 3 times 4 squared minus 12 times 4 plus 9. That gives us 3 times 16, which is 48, minus 12 times 4, which is also 48, plus 9, which gives us 9 meters per second. All right, part C. When is the particle at rest? So if the particle is at rest, it means that the particle is not moving. So what would be the velocity at that point? If it's not moving, then the velocity would be 0. Which, if you think back to the answers we had in part B, one of them was negative, the other one was positive. We can think of the intermediate value theorem. At some point, the velocity has to be 0. So notice this is going to be slightly different than part B. We are not going to find the velocity at time 0. We are going to find when is the velocity equal to 0. So we need to set v of t equal to 0, which means take our velocity function, 3t squared minus 12t plus 9, and set that equal to 0. And for this, we're just going to use some factoring. So first of all, there's a greatest common factor of 3. And I can also factor that trinomial t minus 3 times t minus 1. And obviously I can divide both sides by the 3 that's out front. I don't need to worry about that. This is just going to give me 2 resulting equations. T minus 3 equals 0 and t minus 1 equals 0. Which means at 3 seconds and at 1 second, that is when this particle is at rest. Part D. When is the particle moving in the forward positive direction? So we've already been given a little bit of a clue about this. We had that at 4 seconds the velocity was positive. We would consider that the forward direction. But at 2 seconds, the velocity was negative. So it was moving in the backward direction. What we can also think about is our velocity function itself. V of t equal to 3t squared minus 12t plus 9. That function is a polynomial. It's a quadratic. And maybe if we think about how it is positioned in the coordinate plane, that might give us a clue as to how to answer this question. So on Desmos, I have a graph of our position function and our velocity function. I have the equations to the left over there, but I've hidden the position graph. So what we see here is our quadratic for the velocity function. I have y equal 3x squared minus 12x plus 9, but that's the same thing as v equal 3t squared minus 12t plus 9. And if we zoom in, we'll see at x equal 1 and x equal 3, those are our zeros that we just found. That's where the velocity was equal to 0. And we can see that part of this graph is below the x-axis or horizontal axis. That's the part that's from x equal 1 to x equal 3. And then the other part of the graph is above the x-axis. So we can see that our velocity is positive for all time between 0 and 1, and then also for all time greater than 3. So this function, v of t, is positive just based off of the graph for t between 0 and 1, and for t greater than 3. So those are the times when the particle is moving forward. That's when the velocity is positive. Part E. Use what we found above to draw a diagram that represents the motion of the particle. Now this won't be the graph that we just looked at. This is really a sketch that is just thinking of the particle moving forward and then backward and then forward again and then backward, however that's happening. So to do that, let's just think first we're going to have some sort of line that is measuring position. And there's an initial position where it starts. And then for a certain amount of time, this particle is moving forward away from that initial position. But then at time equal to 1, it turns around. And then it's heading backwards. But then at time equal to 3, it turns around again, and then it continues to go forward from there on out. That's just interpreting the zeros of the velocity function when t is equal to 1 and t is equal to 3, and how it's moving forward. That's where the velocity function is above the x-axis, and then it's moving backward. That's where the graph is below the x-axis, and then it's moving forward again, and it continues to move forward for all time after 3 seconds. The only things that we don't quite know yet are just what are these positions? How far did it get from 0 after 1 second? And then how far did it travel going back to time equal to 3 seconds? And then so on. So we're actually going to answer that in part F. Find the total distance traveled by the particle in the first 5 seconds. So here, we're actually going to break this up. We're going to find the distance for t equals 0 to t equal 1, because that will be a distance that moves positively away from the initial position. And then we're going to find the distance for t equal to 1 second to t equal to 3 seconds, because that's when we're heading in a negative direction. And then we're going to need the distance when we're back moving positively for t equal to 3 to t equal to 5. So for this, all we need to do is just take the positions at all of these times and subtract them. So the distance for t equals 0 to t equal 1 will just be the position at time 1 minus the initial position at time 0. So we're going to use our cubic function, t cubed minus 6t squared plus 9, to figure all these out. So at 1 second, we would get 1 minus 6 plus 9. That's going to be 4. And then at 0 seconds, as no surprise, we have a position of 0. So this would turn into 4 minus 0, or 4. And again, we can just use meters for distance. Then the distance for time equal to 1 to time equal to 3. Again, we would have the position at time 3 minus the position at time 1. So this is 27 minus, that's going to be 6 times 9, so 54. Plus 9 times 3, so plus another 27. And then minus the position at time 1, which we already said was 4. And so then this turns into 27 plus 27 minus 54 is 0. Minus 4 is negative 4. But here, think about this for a little bit. This just means that the particle was traveling 4 meters in the negative direction. So it actually makes sense if we use the absolute value of negative 4. So that way we understand that's how much distance was traveled. It was just in a different direction. And then finally, the distance from time equal 3 to time equal 5. So again, this is s of 5 minus s of 3. We already had that the position at time 3 was 0. We already have that. So all we really need is just the position at time 5, which is 5 cubed minus 6 times 5 squared plus 9 times 5. So that turns into 125 minus 150 and then plus 45. So that gives us 20 meters. So then the total distance would be 4 plus 4 plus 20. So 28 meters. So something that we can learn from this part F is that we do need to pay attention to when these particles are moving in a positive or a negative direction. They're still traveling a distance, so that's why I used the absolute value for the time between 1 second and 3 seconds. We still have to consider that as an actual distance traveled. Part G. Find the acceleration at any time t and at time 4 seconds. So this is first finding a function, a of t, and then after we do that, we're going to evaluate that function at t equal to 4. So remember, a of t is equal to the first derivative of the velocity function. That's the same thing as the second derivative of the position function. So we already have the velocity function, so we need to take the derivative with respect to t of the velocity function, which we said was 3t squared minus 12t plus 9. And that gives us 6t minus 12. And then the acceleration at time 4 seconds would be 6 times 4 minus 12, which would be 24 minus 12, or 12. And remember how we've seen this before. This is meters per seconds squared. So now let's focus on this acceleration function. Part H. When is the particle speeding up? When is it slowing down? So as some descriptions, speeding up means that velocity is positive and it is growing in a positive direction. And also, speeding up means when velocity is negative and it is growing in a negative direction. So, the particle is speeding up when velocity and acceleration have the same sign. On the other hand, slowing down means that velocity and acceleration have opposite signs. We can answer this whole question easily by looking at a graph of all three functions on the same plane. So I'm going to go back to my Desmos graph where I had the position and the velocity so far, and now I'm going to plot this new acceleration function. So I'm going to draw y equal 6x minus 12. So here in my graph, I'm going to type in the acceleration function y equal 6x minus 12. And then I'm also going to show my position function. And I'm going to scale this so we just look at time being positive. So to go back to the beginning, our position function was this cubic function. And notice some of the details that we had before show up, like when time was 0, the position was 0. When time was 1 second, the position was 4. When time was 3 seconds, the position was back to being 0 again. And we could also find out from this graph when time was equal to 5, which was about there, 20 as the position. So then we had our velocity graph, our quadratic, and then now we have our acceleration graph. So to go back to our question that we're trying to answer, we're just focusing on the velocity and the acceleration functions. So back in the notes, first, if we want to find out when is the particle speeding up, that is when the velocity and acceleration have the same sign. So speeding up, v of t and a of t are positive, meaning both graphs are above the x-axis or horizontal axis. And we also have when v of t and a of t are both negative. So let's go back to our graph and see when both of those functions are positive first. So if you look at time equal to 2 seconds, that's when our acceleration function becomes positive. But the velocity function is not positive yet. So only after time equal to 3 seconds do we have both the purple and the blue graph above the horizontal axis. So both velocity and acceleration are positive. That's for time greater than 3. And then when are they both negative? The velocity function is only negative between 1 and 3 seconds. So it has to be somewhere in there. But the acceleration function is only negative before time equal to 2. So this means that our answer for both of them being negative would be between 1 and 2 seconds. So then slowing down, that means that both the velocity and acceleration functions have opposite signs. So meaning one's positive and one's negative. So first of all, we can see that the velocity function is positive from 0 to 1 seconds, but the acceleration function is negative. So that's one instance. And then also, the acceleration function is positive after 2 seconds, but the velocity function is still negative between 2 and 3 seconds. So they have opposite signs between 2 and 3 seconds. And if you think back to our graph that we had sketched out a little bit earlier, just think about we are speeding up and slowing down at certain instances. And you can notice that this idea of slowing down, that was happening as we were approaching 1 second and 3 seconds, which makes sense because that's when we have to turn around. We have to slow down to actually then reverse our direction. All right, so besides physics, we've seen applications with economics when we talked about marginal cost. So for another example, we're going to look at chemistry. In chemistry, a reaction results in the formation of one or more substances, called products, from one or more starting materials, called reactants. In a simple expression, A plus B gives us C, meaning C is produced from the reaction between A and B. The concentration of C is denoted square bracket C, and it is the number of moles per liter and is a function of time. The average rate of reaction would be the difference of different values of C divided by different values of time. Thus, the instantaneous rate of reaction is found by taking the derivative of C with respect to T. For example, if one molecule of the product C is formed by one molecule of the reactant A and one molecule of the reactant B, and the initial concentrations of A and B have a common concentration of the concentration of A equals the concentration of B, and that's equal to lowercase a, just standing for a constant, moles per liter, then the concentration of C at time t is found by this equation. The concentration of C is equal to A squared kT divided by AKT plus 1, where A, again, is the concentration of both A and B, and where K is just a constant. So first, part A, find the rate of reaction at time t. So the rate of reaction, or the instantaneous rate of reaction, would be just the derivative of the concentration of C at time, or with respect to t, which means the derivative with respect to t of that fraction that we have, A squared, where that's just a constant squared, times K, another constant, times T, our actual independent variable, divided by AKT plus 1. So here we're going to have to use the quotient rule. So we have the derivative with respect to T of the numerator times the denominator, and then minus the derivative with respect to T of the denominator, and then times the numerator. And this is all going to be over the denominator squared. So then the derivative with respect to t of a squared kt, again, a squared and k are just constants, and if they're being multiplied by our independent variable t, then the derivative of this whole expression is really a squared k, and that's going to be multiplied by akt plus 1, and then minus the derivative of akt plus 1, that would just be ak, and then the derivative of 1 is 0, so it's just ak for that whole derivative, and that's going to be multiplied by a squared kt. And then we'll distribute in the numerator and combine like terms. So I have a squared, actually a cubed, k squared t plus a squared k minus a cubed k squared t. And this is again over our denominator. And so you can see that we have some cancellation of terms. And so we get that our derivative is a squared k divided by akt plus 1 quantity squared. So that is the rate of reaction at time t. Part B. It can be shown that this derivative that we just wrote down is equal to k times a minus the concentration of C quantity squared. So part B is saying it can be shown that the derivative that we just got, a squared k divided by akt plus 1 squared, is equal to that constant k times a minus the original concentration for C, a squared kt divided by akt plus 1 quantity squared. So you can take a couple minutes and work that out. You'll see how that actually works out. But with that in mind, we then just want to answer a couple questions. What happens to the concentration C and the rate of reaction as t approaches infinity? So let's just write these things down. First of all, concentration C. Again, that was the fraction a squared kt divided by akt plus 1. And then our derivative, concentration of C prime, which was equal to a squared k divided by akt plus 1 quantity squared. We really just want to look at what is the limit as t approaches infinity of our concentration and then the rate of reaction. So let's start with our concentration. So this is asking what is the limit as t approaches infinity of a squared kt divided by akt plus 1. And if you think back to what we did in chapter 2, when we want to find these limits at infinity, we saw that we should divide by the highest power of the independent variable that is in our fraction. So in this case, the highest power of t is just t to the first. So I'm going to divide every single term by t. And I have to do this in the numerator and the denominator. So what we end up with is a squared k in the numerator divided by ak plus 1 over t. And now as t goes to infinity, we saw that something like 1 over t, this will become 0. As the denominator gets larger, 1 over that denominator becomes a very small fraction, meaning 0. So what we actually get for this limit is a squared k divided by ak. And if you cancel out the common factors, we get that the concentration approaches the concentration of the original reactants, A and B. All right, so now let's find the limit of the rate of reaction as t approaches infinity. So we could do the same logic that I just did with what we found in the answer for part A. But what actually helps us a little bit more is that that can also be expressed in this way, which also means we could use this expression. So, if we want to find the limit as t approaches infinity of the rate of reaction, that's the same thing as the limit as t approaches infinity of either the expression that I've circled here, or what I've circled there, or what I have at the very beginning. I can use any one of those, and I'm actually going to use this one because then that can use the result that we just found. So this is the same thing as the limit as t approaches infinity of k times a minus the concentration of C quantity squared. So now let's just use what I just found. We just found that the limit as t approaches infinity of the concentration of C is A, which means this becomes K times A minus A quantity squared, because that was what the concentration of C was approaching. So then this just becomes K times 0, which is 0. Which now when we put all this together, if the concentration is approaching A, that means that the rate of reactions is starting to approach 0.